Good afternoon, everyone. So this will be the third session for the electrostatics, right? We have already finished two sessions for the electrostatics. This will be the third and the final session for the electrostatics chapter, right? So we'll be discussing some of the important questions of electrostatics. So we'll be beginning with the question number one. The question number one says that a particle of mass m and negative charge q is thrown in a gravity-free space, right? With speed u from the point A as shown in the figure, right? On the large charged sheet of uniform surface charge density, let's suppose the uniform surface charge density of this sheet is plus sigma, right? It's a positively charged large sheet as shown in the figure, right? Find the maximum distance from A on sheet where the particle can strike, right? So let's suppose it's given that this particle has been projected at an angle of theta with respect to this point A on the surface of the sheet, right? Now question is that we have to find the maximum distance from A on sheet where the particle can strike, right? Or we can say that we have to find the range of this particle where it can strike on the sheet. Since this is a negatively charged particle, right? We know on the surface of an infinite sheet, the electric field is a uniform electric field, right? It's a uniform electric field having the electric field strength at this point sigma upon 2 epsilon naught, right? So this is the electric field strength due to infinite charge sheet, right? And because of this electric field, once this charge minus q is projected from this point A, there will be a force, electrostatic force on this charge minus q that will be equal to F is equal to q multiplied by the electric field, right? So it's a constant electric field, or we can say the force on this charge will be a constant charge and it will be towards the sheet because of the negative charge of this particle, right? So the magnitude of the charge acting on this particle will be sigma q upon 2 epsilon naught. This will be the net force acting on this charge, right? Net force on this charge. And the direction of this force will be always towards the sheet, right? This is the direction of the force, right? You can see that this charge will behave like the same as we throw a particle under gravity, right, at an angle of theta. And the force acting on this particle is mg, right? The force acting on this particle is mg in the downward direction. If we project this particle at an angle of, if we project this particle at an angle of theta with respect to the horizontal, right? If the particle is projected at an angle of theta with respect to the horizontal with initial speed u, right, at an angle of theta, then the force at any point on this particle is the force due to gravity, right? It's the force due to gravity that's equal to mg in the downward direction, and it's a constant force near the surface of Earth, right? It's a constant force. In the same way, instead of this force mg, the force that's acting on this particle, that's sigma q upon 2 epsilon naught, right? That's sigma q upon 2 epsilon naught, right? Now, once again, this the path of this charged particle will be once again a parabolic path, right? It will be a parabolic path like this, right? So somewhere here, this particle will strike the sheet, right? Somewhere here, the particle will strike the sheet, and this will be a parabolic path, same as that of projectile in a gravity, right? Oblique projectile in a gravity. So in that case, we know that the range of this particle was given as that was u square sine 2 theta over g, right? This was the range of the particle, right? Sine u square sine 2 theta over g, where g was the acceleration, right? Acceleration due to gravity, right? Acceleration due to gravity. Now here in this case, the acceleration will be acceleration because of this electrostatic force, right? It will be acceleration due to electrostatic force. So we can replace u square, it will be u square sine 2 theta as it is. But now it will be acceleration A. This is the acceleration A because of this electrostatic force, right? And this acceleration A will be nothing. It will be a force upon mass, right? Now the force here is sigma q upon m, that's 2m epsilon naught. So this will be the acceleration, right? Now we can substitute the value of a in this equation, right? We'll get sine u square sine 2 theta over a, right? The value of a comes out to be sigma q upon 2 epsilon naught. So it will be sigma q multiplied by 2m epsilon naught, right? So this will be the range, or this will be the maximum distance this particle or this charged particle will strike the sheet, will strike on the surface of the sheet. So r will be equal to u square sine 2 theta, or 2 u square sine 2 theta m epsilon naught upon sigma q. So this will be the range of this particle, or the maximum distance from A on sheet where the particle can strike, right? So it's the same projectile motion, right? It will be a same projectile as that we have the when we project a particle at an angle of theta with respect to the horizontal, and it follows a parabolic path, right, and strikes the ground wire. In the same way, now here the force is a different but a constant force once again at an angle of theta. So it will have a parabolic path once again, right? It will have a parabolic path again, but with a different acceleration. So we just have to do one thing, that we have to replace the acceleration due to gravity, because here the acceleration will be because of the force because of this electric field due to infinite sheet, right? So that's the only difference between the two cases, right? Here the acceleration was acceleration due to gravity, but here the acceleration will be acceleration due to electrostatic force, right? So this will be the range of this particle. Now, moving to the next question, right? The next question is that a simple pendulum of length L and bob mass m is hanging in front of large non-conducting sheet of surface charge density sigma, right? Let's suppose plus sigma is the surface charge density of long infinite sheet. It's a non-conducting sheet, right? If suddenly a charge plus q is given to the bob, right? Suddenly a charge q is given to this bob, right, of length L, right, in the position shown in figure. We have to find the maximum angle through which the string is deflected from the vertical. We have to find the maximum angle through which this string will be deflected. Now you can see here there's a charge Q, and at the same time there will be electrostatic force that will be sigma upon 2 epsilon naught because of this infinite sheet. And because of this, there will be electrostatic force along this direction on this bob of charge Q, that will be force that will be equal to sigma q upon 2 epsilon naught, right? Now you can see here, once this force acts on this bob of charge q, the bob will be deflected, right? It will deflect, and there will be a maximum deflection, right? Maximum deflection, and at this maximum deflection, the net force of this bob will be a zero, right? So the net force of this on this bob will be zero, or we can say that at this position the bob will be at equilibrium. Now we have to find this maximum angle, right? This will be the maximum angle theta here, right? Now this theta we have to calculate, right? I can see here, if this total length here is L, right? If this total length here is L, right? Now you can see from here to here, if this this length is L, right? This length, total length is L, this is theta, right? Now there will be two forces, or we can say there will be three forces, right, on this particle, right? One will be the force because of the string, that will be a tension, it will be away from this bob, right? Another force will be the force due to gravity, that's mg, and the third force will be once again the electrostatic force, that will be sigma q upon 2 epsilon naught, right? 2 epsilon naught. What we can do here is we can just resolve this tension into two components. If this is theta, then this angle has to be theta here as well, right? So this angle will also be theta here as well. So resolving this tension into two components, the one component will be the vertical component, that's t cos theta, right? And another component will be a horizontal component, this will be a t sine of theta, right? T sine of theta, right? Now from here, to decide the equilibrium of this bob here, the net vertical forces should be zero and the net horizontal forces should be equal to zero, or we can say sigma q upon 2 epsilon naught must be equal to the sine component of this tension force, right? That will be t sine theta, and mg must be balanced by vertical component of this tension, that will be t cos of theta, right? T cos of theta. Now if we divide these two equations, we'll get tan of theta. Tan of theta will be nothing, it will be sigma q upon 2m epsilon naught, right? This will be the tan of theta. So this will be the maximum deflection. So theta maximum will be nothing, that has to be equal to tan inverse of sigma q upon 2m epsilon naught. So this will be the maximum deflection for this bob, right? This will be the maximum deflection for this bob because of this electrostatic force, because of this infinite sheet, right? Non-conducting sheet. So this is how we can actually find out the maximum deflection, or this is how we can actually see how we can actually find the equilibrium condition for this bob, right, at an angle of theta, right? We have to just balance all the vertical forces and all the horizontal forces to calculate the angle theta. Now, let's move on to the next question, question number 3, right? The question number 3 says that two thin conducting shells. We have two thin conducting shells of radii r and 3r as shown in figure, right? The outer shell carries the charge plus q and the inner shell is a neutral conductor, right? The inner shell is earth with the help of switch S. Find the charge attained by the inner shell, right? So this is the outer shell here, right? This is the outer shell here. The charge on the outer shell is given as plus q, right? And initially there is no charge on this inner shell, right? But what we do is that there is s switch S connected with the earth. It's in an open state right now. Now if we close this switch S, right, if we close this switch S, the conductor will be grounded, the inner conductor will be grounded. It means the total potential or the net potential on this inner conductor has to be equal to zero, right? It has to be equal to zero, right? So the total potential on this conductor has to be equal to zero. Now let's suppose the finally the charge on this inner conductor is q dash, right? It's q dash. Now the potential because of this q dash will be nothing. It will be kq dash upon kq dash upon the r, right? And the potential because of this outer charge or outer sphere, that will be kq upon 3r, right? And this total potential has to be equal to zero for this conductor because it's earth, right? Now we can see that from k and k will get cancelled, r and r will get cancelled. The value of q dash comes out to be equal to minus q over 3. So it means that net charge on this q dash will be minus q over 3, and this charge will be actually supplied by this earth on the surface of this conductor, right? So the charge supplied by the earth on the inner surface of this conductor will be minus q over 3, so that the net potential on this surface becomes 0, right? So minus q by 3 will be the net charge attained by this inner conductor, right? Now let's move on to the question number 4, right? So the question number 4 is three large plates, right? We have three large plates having have uniform surface charge densities as shown in the figure, right? Find out electric field intensity at point P, right? We have to find the electric field intensity at point P, right? So these are three large parallel plates, uniform surface charge densities, right? We know that the electric field due to the sheet, right, non-conducting sheet, is nothing. That's actually equal to sigma upon 2 epsilon naught is the electric field due to large infinite sheet, right? Large non-conducting sheet. So this is the net electric field due to large non-conducting sheet. So if this is the net electric field due to a non-conducting sheet, right? But we have to calculate the field at this point P, right? So at point P, the net electric field will be because of these three sheets here, right? It will be net electric field will be because of all the three sheets here, right? Now you can see here, because of this sheet of charge density sigma, the electric field will be along this direction, right? It will be along this direction, and its value will be sigma upon 2 epsilon naught, right? It will be sigma upon 2 epsilon naught. Now we have the minus 2 sigma here, right? We have the minus 2 sigma. Because of the minus 2 sigma sheet, the electric field will be towards this negative sheet, right? It will be once again in the downward direction. It has to be equal to, its magnitude will be 2 sigma upon 2 epsilon naught, right? 2 sigma upon 2 epsilon naught. And because of this negative sheet here, once again, this field will be along this direction. Its magnitude will be sigma upon 2 epsilon naught. It means the net field here at this point P will be the summation of these three fields, right? All the three fields are along the same direction, so the net field will be the algebraic sum of the three fields. That will be 2i sigma upon 2 epsilon naught, right? Plus sigma upon 2 epsilon naught. And the third one is also sigma upon 2 epsilon naught. So the net field will be nothing. It will be 3 sigma upon 2 epsilon naught. So this will be the net electric field at this point, right? This will be the net electric field at this point. The net electric field at this point will be 3 sigma upon 2 epsilon naught. Now let's suppose that we have to find the electric field at this point Q, right? At this point Q. Let's suppose we have to find the electric field at this point Q. Now because of this plus sigma here, right? because of this plus sigma here, the electric field will be along this direction now, right? It will be along this direction. And because of this minus 2 sigma, it will be in the downward direction. And because of this minus sigma also, it will be along the downward direction, right? So the net field here will be, the two fields are opposite. Because of this, it will be, now let's suppose that here the net direction in this case will be towards minus k cap, right? It will be minus k cap in vector form. This will be the net direction of the field, right? Net field at the point P, right? So it will be E net at point P. Now finding the E net at point Q, right? So the two fields minus 2 sigma and minus sigma will be along the same direction, so they will add up, right? And the third field, because of this plus sigma, will be in the opposite direction. So the net field will be actually, it has to be equal to sigma upon 2 epsilon naught, right? Minus 2 sigma upon 2 epsilon naught and minus sigma upon 2 epsilon naught, right? So we'll have the net magnitude of this field, that will be sigma upon 2 epsilon naught, right? Okay, here there's a bit calculation error here, right? In this case, 2 and 2 will get cancelled. It will be sigma upon epsilon naught, sigma upon 2 epsilon naught. That will be sigma upon uh, epsilon naught. So it will be 2 sigma upon epsilon naught here, right? It will be 2 sigma upon epsilon naught here, right? So here also 2 and 2 will get cancelled, right? So we'll be left with this sigma upon 2 epsilon naught and minus sigma upon 2 epsilon naught will get cancelled, right? We'll be left with only minus sigma upon epsilon naught, right? And it will be along the k cap direction, that's minus k cap direction. So this will be the net electric field at this point Q, right? Minus sigma upon epsilon naught will be the net electric field at point Q, right? And it will be along negative z axis. It will be along negative z axis. So let's discuss question number 5 here. It's a very important question, right? It's a very important question. The question number 5 is that for the situation shown in the figure below, find potential due to induced charge, right? Where to find the potential due to the induced charge, right? So we'll discuss this case bit in a detail, right? You can see here, we have this hollow neutral conductor, right? We have this hollow neutral conductor, right? In front of this hollow neutral conductor, we have this point charge Q, right? Point charge Q, and the distance between this point charge Q and B is given as D, and the radius of this hollow conductor is R, right? So this is the given information, right? I can see here, because of this point charge Q, there will be induced negative charge, right? Induced negative charge on this surface, right? And there will be induced positive charge as well, right? Positive charge as well. And the charge density of this induced charge will be non-uniform, because at this point the electric field will be maximum, right? And at the rest of the point the electric field will be less. So it means that the negative charge will be more concentrated towards this end than rest of the surface, right? So the charge density will be more at this point, right? The charge density will be maximum at this point. Now, but we have to calculate the potential due to induced charge, right? Potential due to induced charge, right? We know that on the surface of the conductor, the total potential will be a constant, because on the surface of a conductor, the electric field has to fall normal or perpendicular to the surface of the conductor, or we can say the conducting surface or the metallic surface has to be a equipotential surface, right? Then only it can have a the electric field lines will fall normal on the surface of this conductor, right? And since it's a hollow neutral conductor, right? It's a hollow neutral conductor. It means whatever be the potential at the surface, right? V potential at the surface, potential at the surface, or we can write here potential on the surface will be equal to the potential inside sphere, right? Potential inside the conductor, right? Inside the conductor. Since it's a hollow conductor, right? Whatever be the potential on the surface of this conductor, same will be the potential on this inside this conductor, right? Now you can see here there will be some negative charge induced on the surface of this hollow conductor, right? And there will be some positive charge as well induced on this conductor, right? Positive charge will also be induced on this conductor, because the conductor has to be electrically neutral, the net charge on this conductor will be equal to 0, right? We can say Q net on conductor will be 0, right? There will be an induced charge. There will be two poles for this conductor. One side will be negatively charged, other side will be positively charged. But the net charge on this conductor has to be 0 because initially the conductor was electrically neutral, right? Now, where to find the potential on the surface or the potential due to induced charge? What we'll do here is that we'll first find the potential on this surface, right? Potential on this surface, or we know that the potential at inside point is always equal to the potential on the surface, right? It's always equal to the potential on the surface. Now here at this point, the potential here at this point, the potential due to induced charge at this point will be actually the potential due to induced charge here will be actually 0, right? Because each and every induced charge will be at the same distance, and there is same amount of negative charge and the same amount of positive charge. Or we can say here the potential V at R due to V at R due to induced charge, right? Due to induced charge will be equal to KQ net induced upon R, right? So the net induced charge is actually 0, right? So Q net induced on the surface of this conductor is actually 0. So the potential because of this induced charge at the center has to be equal to 0, right? It has to be equal to 0, right? Now the potential at this point R, or potential at this point at the center of the sphere, will be the potential due to this charge Q, right? So the potential due to this charge Q will be the potential at the center, that will be Vc, that has to be equal to KQ over T plus R, right? It will be KQ over T plus R. KQ over T plus R. This will be the potential due to this charge Q at the center, right? The potential due to the induced charge on the surface at the center of the sphere is 0, right? It is 0, right? Now we know that this potential, the potential net potential on the surface has to be the potential at the center, right? Because whatever be the potential on the surface has to be the potential inside, right? Because there exists no electric field inside the conductor, right? So there should not be any potential difference between the surface of the conductor and the center of the conductor. Otherwise, the electric field will not be 0, right? So what we can do here, we have to find the potential due to induced charge. Let's suppose there is some potential due to the induced charge on the surface, right? And there will be potential because of this charge q, right? Also because of this charge q also, right? And let's suppose the potential because of this induced charge v induced, right? Potential because of this induced charge, that will be v induced, and the potential due to this charge q will be kq over t, right? Kq over t, that has to be equal to the potential at the center of the sphere. That has to be equal to the potential at the center of the sphere. That will be equal to kq over T plus R, right? KQ or D plus R. So from here, the potential due to induced charge will be KQ over T plus R minus KQ upon D, right? KQ upon D. So you can get this K and Q common here, right? We'll be left with T minus R upon T into T plus R, right? So from here, T and T will get cancelled. So the net potential in induced because of this induced charge will be nothing. It will be minus KQ upon T multiplied by T plus R. So this will be the net potential. This will be the net potential because of the induced charge on the surface of this conductor, right? This is the net potential because of the induced charge on the surface of this conductor. Now let's move on to this question number 4, right? The question number 6, right? The question number 6 says that 4 charges are placed each at a distance a, right, from origin, right? Each of them are at a distance of a from the origin, right? We have to calculate the dipole moment of configuration. So net dipole moment has to be calculated for this configuration, right? So the net dipole moment because of the discrete charge distribution, right? It's nothing. It's summation of qi ri vector, right? Qi ri vector, where ri vector is nothing. It's the position vector of ith charge. position vector of a charge. Now what we'll do here is that we have four charges. We'll write the position vector for all the four charges here, right? For this 3q charge, the position vector, let's suppose is r1 vector, that will be nothing, that has to be equal to aj cap, right? Aj cap. For the second r2 vector, r2 vector here has to be equal to, for this charge minus 2q, which will be position vector has to be equal to ai cap, right? Ai cap. And r3 vector for this minus 2q charge, it will be equal to minus ai cap, right? And r4 vector for this q charge will be equal to minus aj cap, right? Minus aj cap. So these are their position vectors, right? Now we'll just apply the summation of qi ri, right, for all the four charges, right? The net dipole moment will be, uh, let's suppose for this charge 3q, the charge is 3q and its position vector is a multiplied by j cap, so a j cap, right? And for this charge minus 2q, right? For this charge minus 2q, we have the charge minus 2q and the position vector a I cap, right? Position vector a I cap. And for this charge, we were left with R3 for this charge minus 2 again, right? Charge minus 2. The position vector here is minus ai cap, right? Minus ai cap. And for the fourth charge here of plus q, right? The position vector here is minus aj cap. Now it becomes quite easy to calculate the dipole moment in this way, right? In this fashion. Now you can see here we have 3q aj cap, right? 3q aj cap minus 2q ai cap, right? Plus 2q ai cap, right? And we have finally plus minus q a j cap, right? Now you can see from here. So we'll be left with minus 2k I cap plus 2k I cap. It will get cancelled, right? We'll be left with 3q ai cap, 3q aj cap minus q aj cap. So the net dipole moment will be 2q a along the direction of j cap, right? So this will be the net dipole moment. It means the net dipole moment, because of all the four charges, is actually along this direction, right? It's along this direction, right? So this is the direction of the net dipole moment because of all the four charges here, right? So this is how we can calculate the net dipole moment because of all the four charges here. Let's move on to the question number 7, right? The question number 7 says that two spherical conductors of radii 4 meter and 5 meter are charged to the same potential, right? Two spherical conductors of radii 4 meter and 5 meter are charged to the same potential, right? They are charged to the same potential. They are charged to the same potential if sigma 1 and sigma 2 be the respective values of the surface charge density, right? It's given that sigma 1 and sigma 2 be the respective values of the surface charge densities on the two conductors, right? Then the ratio of charge density is, then we have to find the ratio of their charge density, right? Now we know that on the surface of a conductor, if we have a conductor, let's suppose we have a conductor here, right? And of radius r, right? And the charge q, then the potential on the surface of this conductor will be nothing kq over r, right? Kq over r. Or we can write this as q upon 4 pi epsilon naught r, right? This will be the potential on the surface of this conductor, right? So this is the potential on the surface of this conductor, right? What we can do here is if we just multiply by r in the numerator and divide by the r in the denominator, we'll be left with 4 pi r square epsilon naught, right? 4 pi r square epsilon naught, right? So this will be the what we call as the potential, right? This will be the potential here at this point, right? On the surface of this conductor, right? Now q upon 4 pi r square is the surface area of this surface area for this conductor, right? Or we can replace this charge per unit area. This is the charge per unit area, right? Surface area, right? Multiplied by r upon epsilon naught, right? R upon epsilon naught. Now from here q upon a we can write it as sigma. So sigma r upon epsilon naught, right, will be the potential here, right? Sigma r upon epsilon naught will be the potential here, right? Now from here you can see that if V is constant, right? If V is constant, if V is a constant, then it means that sigma charge density will be inversely proportional to the radius of the conductor, right? Then charge density sigma will be inversely proportional to the radius of the conductor, or we can say that sigma 1 upon sigma 2 will be nothing. It has to be equal to R2 upon R1, right? It has to be equal to R2 upon R1, right? Now sigma 1 upon sigma 2 we have to find out, right? So it will be R2 upon R1, that is 5 upon 4, right? So this will be the ratio of the charge density sigma 1 and sigma 2 for the two conductors, right? So the only concept we used here is just we wrote down the equation of the potential and try to manipulate the equation in terms of the charge density and find the relation between the sigma and R. And we found that the sigma is inversely proportional to the R, provided potential is a constant, right? Potential is a constant. Then sigma 1 over sigma 2 will be equal to R2 upon R1, right? That's equal to 5 upon 4, right? Now, moving on to the question number 8. The question number 8 is the plate separation in a parallel plate condenser, right? So here the condenser means the capacitor, right? Is D and plate area is A. If it is charged to V volt and battery is disconnected, then work done in increasing the plate separation to 2D will be, right? We have to find the work done in increasing the plate separation to 2D, right? It means that we have the capacitor here, right? We have the capacitor here, and this is the capacitor. Initially, the separation between the two plates of the capacitor was D, right? D was the separation between the two plates of the capacitor with area A, right? Let's suppose area is A. It was initially charged to V volts, right? It was initially charged to V volts, right? It was initially charged to V volt, or we can say, let's suppose the charge stored, if the C is the capacitance of this capacitor, right? Then the charge stored in this capacitor will be C multiplied by V, right? This will be the charge stored in this capacitor, right? And the capacitance of this capacitor will be nothing. It will be A epsilon naught upon D. This is the capacitance of this capacitor, right? A epsilon naught upon D. It will be the capacitance of this capacitor, right? Now, what we do here is that we just remove this battery, right? And upon removing the battery, what we do is that we just separate the separation between the, or we increase the separation between the two plates. Now the separation between the two plates is not D, the separation between the two plates is now 2D, right? So 2D is the separation, the area is same, right? The area is same, right? The area is same. And if area is same, right, the separation has been increased, right? The separation has been increased. So what is going to change here? The total charge will be a constant here. Whatever the charge was before, the same will be the charge after, right? Now, what the thing changed here is the capacitance, because we know that the capacitance will depend upon the separation between the two plates, right? If separation between the two plates has been doubled, it means the capacitance will become half, right? So the new capacitance will be A epsilon naught upon 2D, right? This will be the new capacitance, right? It will be the new capacitance, right? Now work done, we have to do work, right? So the work done will be nothing. It will be the final change in the energy stored in this capacitor, right? So initially energy stored in this capacitor was nothing. That will be Q square upon 2C, right? Q square upon 2C, right? That has to be equal to Q square upon 2C. This will be the energy stored in this capacitor, or we can write it as equal to half CV square, right? Half CV square, right? Right? This will be this will be the new, what we call as this will be the new this will be the previous, or the first, the energy present in the first capacitor, that's half CV square or Q square upon 2C, right? Q square upon 2C will be the what we call as energy stored in the capacitor, right? Now the total charge is a constant here, right? The charge before has to be equal to the charge after in the capacitor, because this capacitor is not connected to any external load, so that the charge will be dissipated, right? But here in this case, the new capacitance become A epsilon naught upon 2D, right? A epsilon naught upon 2D, and the total charge has to be, same, right? The total charge has to be same. So it means that the a new energy will be once again equal to Q square upon 2C, right? Q square upon 2C dash, right? 2C dash. Now from here you can see here, if the old capacitance was C, now C dash is nothing, it's C by 2, right? It will be Q square upon 2 multiplied by C upon 2, right? C upon 2, right? it will be C upon 2. From here, 2 and 2 will get cancelled. We'll be left with Q square upon C, right? Q square upon C, right? So we have to find the work done here, right? We have to find the work done. Now we can see here what is the change in energy here, right? So the final energy minus initial energy, right? E final minus E initial will be here. That will be Q square upon C minus Q square upon 2C, right? So it means Q square upon 2C will be the work done, right? This will be the work done, right? So Q square upon 2C will be the amount of work done in separating the separation between the two plates from D to 2D, right? So this much of work done is required to separate the plates of this capacitor from D to 2D, right? Now let's discuss question number 9 here, right? Question number 9 here. The question number 9 says that if the distance between the plates of a capacitor of capacitance C1 is half, right? And the area of plates is doubled, then what will be the capacitance, right? Now let's suppose we have some capacitor of capacitance C. Initially the area was A and separation was D. So the capacitance of this capacitor will be A epsilon naught over D, right? And this was the initial capacitance, that's C1, right? Now what we do is that if the distance between the plates of the capacitor of C1 is half, right? Now the new distance is D dash, that's D over D, and the new area of this of these plates of this capacitor becomes double, right? That's 2 times A, right? 2 times A. So the new capacitor C dash will be 2 times A epsilon naught upon T over 2, right? So it means that it will be 4A epsilon naught upon T. It means the capacitance of a capacitor will become 4 times, right? So the new capacitance of this capacitor will be 4 times C1, or it will be 4 times the initial capacitance for this capacitor, right? So if we double the area of cross section of the plates and half the distance between the two plates, then the capacitance of a capacitor will become 4 times, right? Now discussing this question number 10 here, the question number 10 says that a slab of material of dielectric constant, we have a slab of material of dielectric constant epsilon r, right, has the same area as the plates of a parallel plate capacitor, but has thickness 2d over 3, where it is the separation of the plates. How is the capacitance changed when the slab is introduced between the plates, right? So it's a very good question, right? It's a very important question, right? That's frequently asked in your exams, right? So what happens to the capacitance if we insert a slab into it, right? If we insert a slab into it, right? Now let's suppose if we insert a slab into it, let's suppose the thickness of the slab is T, right? And the dielectric constant of this, what we call as of this slab is epsilon r, right? It's epsilon r, right? Now let's suppose initially the electric field here is E naught, right? E naught, and this E naught will be nothing. It has to be equal to sigma upon, right? Sigma upon epsilon naught, right? Sigma upon epsilon naught. And the electric field inside this what we call as dielectric will be equal to E, that will be equal to sigma upon epsilon naught into epsilon r, right? This will be the electric field in this dielectric, right? I can see here, or you can write this E will be nothing. It will be E naught by epsilon r. This will be the electric field, right? This will be the electric field inside this uh, dielectric, right? Inside this dielectric. Let's suppose this is the battery connected to this capacitor connected to battery potential V, right? Now from here, what we have to do is that there will be some potential drop in this region, right? And there will be potential drop across this dielectric slab, right? And the electric field is a uniform inside this dielectric slab as well. It's E naught upon epsilon r, right? So the total potential V will be it will be E naught, right, upon epsilon r, right, multiplied with the thickness T of the slab, right? The remaining thickness of this, let's suppose the separation between the slab is T, the remaining thickness will be D minus T, right? So we'll be left with E naught, right, E naught D minus T, that will be equal to V, right? So from here, the value of E naught is nothing sigma upon epsilon naught, or we can write it as Q upon A epsilon naught into epsilon r, right, multiplied by T, right? It will be Q upon A epsilon naught, right? Q upon A epsilon naught, right? D minus T, right? D minus T. Now from here, the capacitance will be nothing. It will be the total charge of this capacitor, or the total charge of the plates of this capacitor, Q upon V, right? Now replacing Q is as it is, replacing V with Q T upon A epsilon naught into epsilon R, right? Plus Q upon A epsilon naught multiplied by D minus T, right? D minus T. Now from here, Q and Q will get cancelled. We'll be left with, if we take 1 upon A epsilon naught as common, it will be A epsilon naught right here. It will be A epsilon naught here. We'll be left here with T upon epsilon R, right? Plus D minus T, right? Plus D minus T. So T upon epsilon R plus D minus T. So this will be the capacitance, right? So A epsilon naught upon, so it will be, we can just take T common from this, right? It will be T plus, taking T as common from this, we'll be left with 1 upon epsilon R minus 1. So this will be the capacitance of this capacitor, right? So new capacitance of this capacitor will be A epsilon naught upon T plus 1 upon epsilon R minus 1, right? Multiplied with the thickness T, right? Multiplied with the thickness T here, right? Thickness T. Now we can just substitute the thickness of this slab, right? That's 2D over 3. Can put the value of this thickness here 2D over 3 and to calculate the capacitance, right? So this is how the capacitance of a capacitor is changed upon introducing a slab of thickness T, right? This is how the capacitance of a capacitor changes upon introducing the slab of thickness T, right? Now let's discuss last question for this session, right? So with this last question, we'll be finished with the electrostatic portion, and in the next lecture, we'll be starting with the magnetic field, right? Magnetic field due to charge, right? That will be then started from the next session, right? There will be 3 sessions for that magnetostatics overall, right? First will be the magnetic fields due to wires, right? And the second will be the magnetic field due to charge, and the third one will be uh, the magnetic different instruments, like we have ammeters, we have galvanometer, right? We have a moving coil galvanometer, right? All these instruments will be discussed in the third session, right? And then we'll be starting with the electromagnetic induction and AC, right? So let's discuss this final question, last and final question with respect to the electrostatics, right? That's the capacitors in series, right? So in this question, we have been given 3 capacitors and charged capacitor connected in series as shown in circuit with battery of EMF 30 volt. Find out following. We have to find charge flow through the battery, right? We have to find the charge flow through the battery. So what it means, what amount of charge supplied by the battery, right? You can see here. Uh, the equivalent capacitance of these capacitors, all the 3 capacitors are in series, right? All the 3 capacitors are in series, and each and every capacitor will have the same amount of charge, right? Because they are placed in series, right? So 2 microfarad, 3 microfarad, 6 microfarad, all the 3 capacitors will have same amount of charge, right? So the charge supplied by the battery will be the equivalent capacitance of this what we call as 3 capacitors, right? Multiplied by the potential, that's 30 volts, right? The equivalent capacitance for these 3 capacitors will be nothing, that will be 1 upon 2 plus 1 upon C equivalent will be 1 upon 2 plus 1 upon 3 plus 1 upon 6, right? So it will be nothing. So we'll be left here with it will be 3 upon 6, right? 3 upon 6 plus 1 upon 2, right? That will be equal to 6 upon 6, right? That will be equal to 1 microfarad, right? 1 microfarad, right? So 1 upon 1 microfarad will be 1 upon C equivalent, or C equivalent will be equal to 1 microfarad, right? 1 microfarad will be the equivalent capacitance for this capacitor, right? The charge supplied by this battery will be nothing, Q, that will be C equivalent multiplied by the potential difference of this battery. C equivalent is 30 volt, right? Multiplied by the potential difference of this battery, that's 30, right? So 900 coulombs, right? 900 microcoulombs, right? This will be the charge supplied by this battery, right? So this much of charge will be supplied by this battery. Now the potential energy is stored in 3 microfarad, right? It's a 3 microfarad capacitor, right? So the energy stored in the 3 microfarad capacitor will be nothing, right? It has to be it has to be we can find out the potential on this capacitor, right? Or we can if this is a 30 microcoulomb 30 volt supply of this battery, right? And this same amount of charge will be on each and every capacitor, right? Because the total charge supplied by this battery is 900 microcoulomb, so same amount of charge will be on all the three capacitors, right? Or all the three capacitors, right? So the energy here will be nothing, it will be q square over 2c, right? Q square over 2c, right? So you can just substitute the value of Q and C in this equation, right, to calculate the potential energy in the 3 microfarad capacitor. So U total in all the capacitors. So the U total in all the capacitor will be nothing. It will be half C equivalent, right? V square, right? Now the C equivalent is nothing. That's 1, and V is 30 square. That will be 30 square. That will be 450, right? It will be 450, right? 450, it will can be 450, its equivalent is here equal to micro, right? That's microfarads, right? It will be equal to microjoules, right? So this much of energy will be here, right? 450 microjoules, right? Now heat produced in the circuit, right? So the heat produced in the circuit will be the total energy supplied by this battery, right? Total energy supplied by this battery. So the total energy supplied by this battery will be C equivalent, right? It will be CV, right? CV square will be the total energy supplied by this battery, right? The total energy supplied by this battery, right? So work done by this battery will be C V square, right? Or we can write it as 1 C equivalent V square. That will be C equivalent is 1. It will be 900, right? That's equal to 900. So the total heat generated here will be 900 minus 450, right? This much of heat will be actually generated. That's equal to 450 microjoules, right? 450 microjoules. So this much of heat will be actually whatever work is done by the battery, right? Half of that work done is actually converted into the, or we can say liberated in the form of heat energy, right? Or dissipated in the form of heat energy by the battery, right? So 450 microjoules has to be the heat generated or heat produced in the circuit, and the total energy stored in the circuit will be also equal to 450 microjoules, right? So this is it with respect to the capacitors and electrostatics, right? So we are finished with the electrostatics portion. In the next lecture, we are finished with the electrostatic portion. In the next lecture, we'll be starting with the new chapter that will be magnetostatics, right? Or the electromagnetism, right? So there will be discussing the magnetic field due to different conductors and magnetic field due to charge as well. So that will be done in the next session tomorrow, right? Till then, take care and goodbye.